instantaneous rate of change. So far, we've looked at a couple different types of rates of change, and we said that part of the reason that we want to study change is that we want to be able to use functions to predict what might happen at a later time. So far, we've looked at the relative rate of change and the average rate of change. So we're going to build upon what we know about the average rate of change to figure out what's called the instantaneous rate of change. So let's review what we know about the average rate of change. So the average rate of change tells us how much a function changes on average between 2 points. We look at the slope of the secant line and we use the formula f of b minus f of a over b minus a. When we do this, we're always looking between 2 points, and the result we get is something that's happening on average. What we want to do is we want to use this average rate of change to tell us about what's called the instantaneous rate of change. So the instantaneous rate of change is how much a function changes at 1 point. This is really powerful because if we can find out how much a function changes at 1 point, we can look at cumulative points to find out exactly how much a function changes on an interval instead of the average. We calculate the instantaneous rate of change by finding the limit of average rates of change of f of x over smaller and smaller intervals around a point A. So what that means is we want to look at a specific point that we're interested in. We're going to look at the average rate of change near that point, and we're going to see what the average rates of change are approaching as we get closer and closer to A. So we're going to look at some visual representations of this, but before we do, let's try to imagine what the difference is between average rate of change and instantaneous rate of change. A good example of this is driving your car. So consider that it takes you 3 hours to travel 150 miles to your cousin's house while you drive. Your average rate of change would be 50 miles per hour. Because if we look at the per hour travel, we went 150 miles over 3 hours. That's how much you changed on average. Now, your instantaneous rate of change is going to be the speed that you're going at any given moment. So if you're driving to your cousin's house and you look down at your odometer and it says you're going 75 miles per hour, that's your instantaneous rate of change because at that moment, that is how quickly your position is changing. So instantaneous rate of change is really what's happening at one particular moment. And we're going to use average rates of change to be able to calculate or to get a good approximation of this instantaneous rate of change. This is a method we use a lot in mathematics where we use something we know to try to figure out something we don't know. So we're going to start with a visual representation of this average rates of change to approximate instantaneous rates of change. So the example that we're going to use to motivate and visualize what's happening is the function 0.5x squared, which is the blue graph given below. Now, in this particular example, we want to try to approximate the instantaneous rate of change at -1. So at -1, we want to know exactly how much the function is changing. So what we're going to do is we're going to look at average rates of change near -1 to help us approximate. And this is how this works. So we're going to approximate the average rate of change to the left of -1 and to the right of -1. So when we do this to the left, I'm looking between the points -1 and -2. So I'm going 1 unit to the left. And when I approximate the average rate of change, I'm going to do f of b minus f of a over b minus a. So here, I'm going to be doing f of -1 minus f of -2 divided by -1 minus -2. Be careful with your negatives here. So for this particular function, when I plug in a -1 into my function, I'm going to get 0.5 minus, and if I plug the -2 into my function, I'm going to get 2 divided by, now -1 minus -2. The minus and the negative are going to cancel, and I'm going to be left with a 1 on the bottom. So crunching that number is going to give me -1.5. So the slope of this line, the average rate of change between -2 and -1, is -1.5. And again, just for reference, when I calculated f of -1, I took -1 and I plugged it into the function to get the y value of 0.5. Now, I'm going to do the same thing, but I'm going to do it to the right of -1. So here again, I did the left in red. So now I'm going to do to the right of -1 in green, so we can see what the slope of that line is going to look like, again, using average rates of change. So to the right, I'm using the point 0 and x equals -1. So I'm going to do f of 0 minus f of -1 divided by 0 minus -1. So f of b minus f of a over b minus a. Now, it's not a coincidence that I went 1 unit to the left of -1 and 1 unit to the right of -1. I want to be consistent in how close I am to -1. So since I went 1 unit to go to -2, I also went 1 unit to go back to 0. So plugging these numbers in, f of 0, if I plug 0 into my function, is going to give me 0, minus f of -1 is 0.5, divided by, now on the bottom, the negative and the minus are going to cancel out. So divided by 1 gives me -0.5. So the slope of the line between -1 and 0 is -0.5. So what does that tell me about how much the function is changing at -1? So what that tells me is that my instantaneous rate of change, which is what I'm looking for here, has to be between -1.5 and -0.5. This is going to give me bounds as to where my instantaneous rate of change needs to be. So we can see that there's about a 1 unit difference between -1.5 and -0.5. So what we do, as we said before in our definition, is we want to take the limit of these average rates of change as we get closer and closer to -1, or as we get smaller and smaller intervals around -1. So if we want to get smaller and smaller intervals, we want to repeat this, but now instead of going 1 unit away from -1 in either direction, we want to stay a little bit closer. So let's look at the next picture here. So now we have the same function, 0.5 x squared, but now when we look to the left and the right, instead of going 1 unit away, we're going to go 0.5 units away. So we're getting closer to -1. So when we do the average rate of change to the left, we're going to be using the point -1 and -1.5. So we're going to do f of -1 minus f of -1.5 divided by -1 minus -1.5. So again, we're finding the slope of the red secant line. We're doing this rate of change to find what's going on here. So we said f of -1, we're going to plug in again to the function here, is going to give us 0.5 minus 1.125 divided by, now on the bottom we have -1 minus -1.5. Again, the minus and the negative are going to cancel, and that's going to give us 0.5 on the bottom. When we plug that into our calculator, we get -1.25 for our slope of the average rate of change to the left of -1. The slope of that secant line is -1.25. Again, we also want to calculate the average rate of change to the right of that point. And when we do it to the right, we're also going to go 0.5 units. So now we're going to do f of -0.5 minus f of -1 divided by negative 0.5 minus negative 1. So again, we're going to take these numbers and we're going to plug them into our function. When we plug in negative 0.5 into our function, we're going to get 0.125. So 0.125 minus, when we plug in a negative 1, we get 0.5 divided by, now again on the bottom we have minus and negative, so those are going to cancel. So we're going to divide by 0.5. When we crunch that number in the calculator, we get negative 0.75 as the slope to the right of negative 1. Now, in the last example, when we were 1 unit away, we were 1 unit apart in terms of where our interval was. So we can see that our interval is a little bit smaller because now our instantaneous rate of change has to be between negative 1.25 and negative 0.75, which is only a 0.5 interval length. Before it was a 1 unit interval length. So the closer we get to negative 1 with our approximation, the smaller our interval is where our instantaneous rate of change needs to live. Turns out, if we get closer and closer and closer, eventually the average rate of change on the left is the same as the average rate of change on the right. And when that happens, the slopes of those two lines are the same and they become one line. If we were to do that with this particular example, what would happen would look like this. So the average rate of change on the left would approach negative 1, and the average rate of change on the right is approaching negative 1, and eventually they both reach negative 1. So that means we have one line now, and it has a slope of negative 1. And that one line touches at the one point that we were interested in, right here at negative 1. And so we know then that the instantaneous rate of change has to be negative 1 because that's what both sides approached as we get closer and closer to negative 1. Turns out that this line has a special name and has special meaning. Remember that the slope of the secant line, which was a line that connected 2 points, was our average rate of change. This line is called the tangent line. The tangent line is a line that touches a function at a given point, so at one point. The slope of the tangent line is the instantaneous rate of change at that point. So again, we used secant lines, which gave us the average rate of change, and eventually they became one line, which we then call the tangent line. So one of the main differences here is that secant lines connect 2 points. Tangent lines touch at 1 point. Both of them, however, we evaluate the slope to tell us how much the function is changing. The slope of the secant line gives us the average rate of change, and the slope of the tangent line is going to give us the instantaneous rate of change.